We're now going to look at names that we use for various different shapes in the course, two-dimensional shapes. So we're talking about closed figures called polygons. A three-sided polygon, well, you know that to be a triangle. If it has four sides, it's called a quadrilateral. And from then on, we use the Greek number and the Greek name end gon to say how many sides a figure has got. So pentagon, Greek for 5 is penta. Hexagon, Greek for 6 is hex. Heptagon, because the Greek for 7 is hepta, and so on. Octagon, nonagon or enneagon. A decagon, a 12-sided figure is called a dodecagon. A 25-sided figure is called an icosagon, and a many-sided figure is just called a polygon. Poly means many. Useful ones for you to really be sure of here will be 3, 4, 5, 6, and 8. And the others are of interest mainly rather than anything else, but it is worth committing some of these to memory. So here's an example of a polygon. If we count the number of sides, 1, 2, 3, 4, 5, 6, we note that this is a hexagon. We can label the vertices, and we want some various terms to describe a polygon. We could name this as A, B, C, D, E, F, just reading clockwise around the figure in alphabetical order. That seems sensible, but there's nothing to stop us starting, say, at B instead. B, C, D, E, F, A. Or we could go backwards from a completely different point, D, C, B, A, F, E. All of these are completely viable, and there are obviously very many of them. The important feature is that you're always going consistently, either clockwise or counterclockwise around the figure until you get back to where you started. You don't repeat the start and end, so we don't call this A, B, C, D, E, F, A. The first and the last one are assumed to join up to complete the figure. Points are called vertices, and if you have two vertices that are next to each other, we call those consecutive vertices. So C and D are next to each other in the order. They're consecutive vertices. The line segment joining consecutive vertices is called an edge. If you join two vertices that are not consecutive, say A and D, that line segment is called a diagonal. There are obviously very many diagonals within this figure. If the polygon has all the diagonals lying entirely inside it, then it's called convex. If it's convex, all of its interior angles will be less than 180 degrees, like we got here. And if you think about walking around this figure, if it were a building, you'd notice that if we walked clockwise around it, we'd just constantly be turning right, or if we walked counterclockwise around it, we would at all points be turning left. This polygon over here, not quite such an attractive one. In this polygon, we've got a diagonal that passes outside the shape. It's called concave, therefore, because it bends in. It's got a dent, a concavity. If you've got a concave polygon, you can also know that because at least one of the interior angles will be a reflex angle. And if you think about walking around it, if it were a building of some sort, you'll note that sometimes you'll be turning left, sometimes you'll be turning right if you're following the walls all the way along. If you shortcut, you'd be using one of the diagonals instead. So here are some rather more routine-looking polygons, more standard-looking ones. This one has all 6 angles the same. A polygon with all the angles the same, or all the interior angles the same, is called equiangular. And we should use the proper word congruent to say that these angles have the same size. Angles can be congruent. This figure, all 4 of the edges have the same length. So all the edges are congruent on this because remember an edge is just a line segment. So if we're saying they're the same length, we're saying that the segments are congruent. And a polygon whose edges are all congruent is called equilateral. If a polygon has all edges congruent and all angles congruent, so it's equiangular and equilateral, it is called a regular polygon. This here is a regular heptagon. It has 7 sides, all the angles and all the side lengths are the same.